Hello everyone. I am Thibault and I will present you the work I did with Francois Berard. We are from Université de Grenoble. So last year, head-mounted displays, both opaque and see-through ones, became widespread. The purpose of those devices is to immerse you into a virtual world. For the immersion to be complete, the user must be able to interact with the virtual environment as if it was his own environment. One way to do this is by adding an avatar into the virtual world, like the virtual hand in this example, that would exactly replicate the user's physical movement. This technique is called isomorphic mapping. In everyday life, we are used to interact with a lot of objects. We can even perform some tasks with closed eyes, thanks to proprioception, like drinking a glass of water, for example. A previous work from mine already exploited proprioception in virtual environments. So isomorphic manipulation aims to benefit from this enormous user practice by replicating physical world manipulations. That's why we decided to work on this kind of interaction. Our main contribution is a user study set up to evaluate the performances of several isomorphic systems. To do so, we choose to implement a docking experiment. A docking task is, for example, to put this purple object into the gray area. In space, it's a 6 degrees of freedom task, 3 for the position and 3 for the orientation. In previous work, we studied an isomorphic interaction that has never been tested in a docking task. It is the Handheld Perspective-Coupled Display, introduced by Stavnes 7 years ago. The main idea of HPCD is to display images on manipulable objects depending on the user position to make the illusion that virtual contents are inside the device. Our previous work shows the potential of a lightweight and wireless implementation based on stereoscopic projection. The user here only uses shutter glasses. Let me show you what you can do with HPCD. So here you can see the user exploring an object and his view on the corner recorded by a camera added on the shutter glasses. Even without stereoscopy, you see the 3D effect that works only from the user point of view. HPCD can take any form to adapt to the object you want to manipulate. In this example, we use 2 HPCD. Lightning on the planet depends on the sun position. And you can also play with projected shadows. Or you can move around the object to explore either during nighttime or during daytime. Now, what about the literature? In the past year, there have been some studies over 6DOF tasks involving midair interaction. Weber results shows that they are less accurate than a phantom, and a work from Besançon shows that they can be faster than a mouse. Given those results, we decided to include the phantom as a state-of-the-art condition for our experiment, but with not so much conviction. Indeed, in all the study we read, the tasks evaluated were different, and we can't know for sure if the results can be compared. And that is a great challenge when you work in docking. We test some easy tasks, some harder ones, and we try to generalize our results, but we have no metrics to do so. In the field of 2D positioning, for example, there is an isonorm based on the Fitts law that ensures studies correlation. We need a metric for the docking experiment to compare future studies. And as a secondary contribution, we propose in this paper a first step in this direction, based on an adaptation of the Fitts law. So what is the Fitts law? A quick reminder. We know that reaching a close and wide target is easier than reaching a small and distant one. For 1D tasks, Fitts quantified this difficulty and demonstrated that the time needed to complete a task is linear to its index of difficulty. You can then extract an information throughput from those slopes, which theoretically do not depend on the task chosen during the experiment. With some symmetries, it's easy to adapt this law in 3D, and so it's widely exploited for 2 and 3DOF analysis. But it does not combine rotation and translation, so it can't be used for 6DOF analysis docking. Nevertheless, work from Stolen shows that a combined 2D index can be computed as the sum of 2 1D indices, but the sum of 2 3D indices was never computed. We started from here, and with the classic Fitts formulation, it gives this formula. The A and alpha distance parameters are easy to adapt, so we will focus on the target size parameters. The ID, so, is function of a position width W and a separated angular width omega. This separation does not make sense for us. For example, in this checkbox game, you have to make a trade-off between precision in position or in rotation so that overall the object fits in the hole. Rotation and translation error are correlated, and we want to keep this strong relation in our target size definition. So let me introduce you ET, the error tolerance. ET is a spatial margin around the perfect target, here illustrated in 2D. The target is reached when the object is entirely inside the red area. This way, there is place for a small translational error and some more place for a small rotational error. Of course, rotational error here is homogeneous to a distance and is a function of the manipulated object size and the angular error. The target is reached if the sum of those errors remains inferior to ET, giving this second formula. But the final ID depends on how ET is shared between W and omega. To solve this system, we make the assumption that humans are smart, or at least they are lazy, and so they will instinctively solve the task in the easiest way possible, that is the one who minimalizes the ID. That's how we define the ID of a task depending on its amplitude parameter and its error tolerance, ET, which will allow us to compute 6 DOF information throughput. So now let's go back to our main contribution, user studies that compared 4 isomorphic interaction systems. We asked participants to put a red chair into a target area, the gray target area, pointed by an arrow. Part of the chairs that are inside the area turn green, and when the chair is all green, the target is automatically validated, and the next one appears. We tested 4 conditions. First, the state-of-the-art, an articulated arm, a phantom omni, was used alongside a 7:10 ratio flat screen, 60 centimeters wide. Here you can see me solving the task. For all other conditions, we used a 50 centimeter radius sphere as the input device. The purpose of the prop condition was to isolate the benefits of this input metaphor, and so it was used alongside the same screen. The third condition immersed the user into a virtual world where the chair was located exactly at the position of the sphere in the real world. We use a OSVR SDK2 HMD, and you can see the user view in the corner. The final condition is the HPCD as presented earlier, with the virtual chair fixed inside the sphere. In a concern for internal validity, all conditions were rendered in stereoscopic 3D with head coupling, and all devices were tracked using the same OptiTrack system. There were 5 targets chosen to offer good ID repetition following GIA guideline. We welcomed 20 volunteers in a within-subject design and recorded 2 blocks of 10 repetitions of 5 targets for each condition for a total of 8,000 dockings. So, what are the results of this experiment? This figure presents the mean docking time for all conditions. All tasks are grouped whatever the difficulties. All results are presented with 95% confidence interval, and we observe clear differences. The ANOVA and all periodicity tests were significant. So prop overperformed the phantom condition by nearly 20%. HMD overperformed prop by 12%. And the most impressive and unexpected, HPCD overperformed the HMD condition by 17%. So let's take a closer look. In this figure, we separated the previous results per ID. Those results reflect the previous one and are quite aligned, except for this value, clearly out of alignment. We believe that this incoherent result is due to ergonomic limitation of the task chosen, which asked an uncomfortable and difficult movement of the wrist with the phantom only. So we ignored this value and we computed the regressions. They are presented here with the R-square values for each slope, all superior to 0.9. So we can compute the information throughput for each condition. As you can see, the results are consistent as HPCD presents a throughput 1 byte per second better than HMD, and 2 compared to the state-of-the-art condition. This study seems to validate the 6DOF index of difficulty that we proposed. Moreover, the throughput funds are quite similar to those reviewed by Sukorev and McKenzie over 2DOF works. These are encouraging results that hail for replications. So let's try to explain the differences observed between the devices. Why is probe faster than the Phantom? We understand that a two-handed input is more stable and more accurate than a one-handed one. So that explains the result for us. Why is HMD faster than the probe? Where and Rose demonstrated the importance of a direct interaction for rotation control. So we believe that the indirection of the probe condition explains its lack of performances compared to the other techniques using the same input. Now, HPCD superiority over HMD is an unexpected result, as it was exactly the same movement of the sphere as to the user. So let's take a look to the HMD limitations. First, resolution remained quite low in today's HPCD, but probe resolution is the same as HPCD, and it does not prevent it to be outperformed by the HMD. A subjective questionnaire revealed that HMD was fundamentally painful by several users. But other users didn't report this discomfort and still better performed with HPCD. Finally, HMD condition was poor in contextual information. Contextual information is all the surrounding information that can help the user to solve the task. In the HMD, we only incorporate a basic ground plane corresponding to the floor. It's this strange gray shape here. It gave the user a minimum referential, but in HPCD, all the room information, the sphere, and even the user body and arms and hands were visible. So does it help? This figure presents a typical error correction curve over time. We identified two phases, the first fast one that could be done with closed eyes, thanks to proprioception, and the following correcting phase that needs precise and a lot of visual feedbacks. And here you can see the time spent in each phases for the two conditions. The largest part of the gain by far between HPCD and HMD happened during the precision phase, which tend to confirm that the lack of contextual information with the HMD slowed down its performances. As perspective for future works, we come with two questions. First, will future HMD solve those technical resolution and comfort issues, and will it have an impact on the performances? Second, to really validate our main hypothesis, it could be interesting to add as much contextual information as possible into the virtual world. Still, HMD offers a wider field of view than HPCD. This difference did not impact this experiment as we designed it, but future works should question whether they need a large field of view or rich contextual information to choose between the two solutions. So what to remember of this talk? We tested several isomorphic interaction systems in a 6DOF task and showed that HPCD was 17% faster than HMD, which was itself faster than a tangible probe, itself faster than the Phantom state-of-the-art condition. We also presented a new index of difficulty to compute devices throughput for 6DOF tasks that can be used to compare devices across future studies. In the end, immersion is cool, but in some cases, keeping the user real environment alongside the immersive virtual world can be even better. Thank you very much.
Hello, Diego Martinez from Sussex. Something that I found a bit surprising in the HPCD condition, you could only see whatever was projected on the sphere, right? So if my target was actually over there, I would end up like searching for it. I'm wondering what was the impact on the task? Was that more exhausting for the people? I don't know, I just found it a bit surprising.
Yeah, good question. in the experiment, as we designed it, we did not put a lot of different targets. There were 5 different targets, and one of the purposes was to allow proprioception and spatial memory so that the user can remember all the targets. So in quick training phases, they knew where the targets were positioned, so the focus came when they were close to the target. And when they were not close to the target, there was this arrow that pointing the direction. Okay. But yeah, that's a great difference with HMD, where you have a full, more than 100 degrees of field of view, and that's a great difference between the 2 techniques.
No, it's the same. The one with the clock, you've got the full screen, so I know I'm going to go.
Yeah.
Okay.
Hi, Rob Tether, Carleton University. Thanks for the nice talk. This is cool stuff.
Thank you.
I wanted to ask, could you, I might have missed this, you might have said this, but I might have.
Sorry?
How did you calculate your throughput scores?
We use the Mackenzie technique.
So this is applying the accuracy adjustment then? Effective width and things like that?
Sorry, I didn't understand you.
Was this using the accuracy adjustment proposed by SIGCHI, well, not proposed by, but you cited the SIGCHI and Mackenzie 2004 article, and that they talk about this method of effective width and effective distance.
Yeah.
And you applied that?
Yeah.
Okay. Thanks.
Thank you.
Hi, Florian Diver. Nice talk. I wonder, have you visualized the hand in the HMD condition? Or
No.
not? Do you think this might make a difference? Because then you also might have different kinds of feedback, and maybe this brings it also more to HPCD, or what's your thoughts on this?
Yeah, so in the HMD view, you mean? That's the HMD view. We only have the target and the ground plane texture as the floor, and we didn't add anything else. And yeah, that's our guess, is that the lack of contextual information, for example, the end, explain a lot of the differences observed. So it could be a future work to try to add as much contextual information, and even to try to find out which contextual information is the most important for this kind of task. For example, maybe I don't need to have the wall of the room, but maybe it gives me a depth information. So yes, it's a good perspective.
Just a quick follow-up question. So in your HPCD condition, you see that you're holding a sphere, with a chair fixed within the sphere. And in the other 2 conditions, in HMD and prop, you're interacting indirectly, but you're holding something which is quite different from the chair which is presented. So that's made for very different proprioception. Do you think it might affect the mental model for the docking tasks, and the user interacted in different way in HPCD and Handheld condition?
So you mean that maybe we could use a different HPCD with a clone?
Or different object, or for the HMD condition, just another object which resembles a chair.
So we use the same sphere for all conditions for concern of internal validity. And as it was mentioned in the earlier question, we still need to have some, at least a good field of view in where we focus. So that's why we have a large sphere. So for the HPCD is what it was quite useful to have a large sphere to see.
Yes, but for the prop or the HMD condition, it's quite.
Yeah, it's too. Maybe for the prop, it's too. It will be easier with a smaller smaller sphere, but I'm not so sure because maybe a small sphere you can have it with one hand and not 2 hands. So I guess it will be less precise.
Okay.
Thank you very much.
Okay, let's